numbers, random numbers, which has been generated from a physical process. And the principle of the physical process is based on the theory of quantum mechanics. Then the word distribution. I do have, to say something about it, because I think it is more of a generation than a distribution. In conventional PKI, public key infrastructure, or any cryptography, what we do is we generate the keys and then we distribute it from one person to the other person who wants to decode the message. So we have to transfer the key, and this will be discussed in these slides also. But just since I would want this thing to be very clear with everybody, what actually we are looking for, what we will be studying in this presentation. So distribution is so the distribution, you can don't take it, literally. Please understand that what we will be discussing today is generation of encryption, decryption, or cryptographic keys spatially separated using quantum communication. Okay. So here I have listed some of the preliminary cipher devices to tell you that as society changes, as society is developed, as the technologies are introduced into the society, our cipher devices have also seen, have been impacted. The cryptography has been impacted. For example, in 400 BC, we had this skytail, and here it's understood that, and we have also seen movies on it. They use the method of transposition. Okay. Then we have the Caesar cipher, the famous, cryptography here, and here we use substitution method. And basically, the substitution method is more popular, and in some form or the other, there are a lot of playing kits also available, and it's very commonly used. Then, as and when the society developed, you made it a little more complicated by introducing some more variables. And in 20th century, we had this electromechanical device, Enigma. Now, and then to decode the cryptography, we needed another electromechanical device, bomb. Okay. So, and in this time, when we're talking about quantum technology, we will be doing the encryption using the quantum mechanics, and this technology or this art is considered to be information theoretic secure. If you look at the skytail, Caesar wheel, whatever cryptography we do on it, it can be decoded using our conventional laptops. Enigma, maybe you would need some more computational power. So in this manner, you try to make it more and more complex. So you keep on increasing the hardness of the problem, and you will, if you have access to resources, you will be able to solve it in a faster time. Now, this is all classical cryptography. When we talk of quantum cryptography and a quantum computer, you have access to a higher computational model. So the problems which can be solved in a classical supercomputer in some billions of years, in a quantum computer, it can be solved in polynomial time. And that is the primary reason why we all are, discussing this topic today, because we now need to transition to quantum security. Now, this is interesting to know that, if you are doing the quantum security, then it is information theoretic secure, which means that even if you have lot of resources, memory, time, still you will not be able to break the code. This is a general architecture of cryptography, where you the person Alice wants to send a secret message to Bob. For example, say, "Hi, Bob." So she will be using an encryption key, and that key has to be communicated at the other end. So you have the decryption key. If it is asymmetric, so we are talking about symmetric key cryptography. Okay, in asymmetric key cryptography, particularly the public-private key, so it follows a different, a more pragmatic approach. But in this session, we will be more focused on the symmetric key cryptography, which means the encryption and the decryption keys are similar. Okay, so now one has to send the key from one place to the other, and there lies the challenge. Okay, now when we are discussing this particular algorithm, encryption algorithm, one-time pad, before that, let me tell you that in today's world, everybody or all the adversary, or we know it's publicly announced what are the encryption and the decryption algorithms are announced publicly, right? So what is so the entire secrecy of the communication system lies in the encryption and decryption keys. Okay, I had told you about the information theoretic security model, right? So the one-time pad is an encryption algorithm which is information theoretic secure, provided it uses random enough numbers. They should not be reused, and the numbers are as long as the message. So you already have an encryption algorithm, but you need to now send the key from one place to the other. That is why in the first slide it was written distribution. But what actually we do is key generation, and we will be seeing that in subsequent slides. So the challenge lies in how to communicate the encryption, the cryptographic key from one place to the other. This is the challenge which QKD tries to solve. Okay. As you can see here, that there is no secure means defined in the classical world, where it tells you if your if your key has been copied, cloned, pictured. You will not be able to know about it if your keys are pictured, copied, cloned. It's a classical device and you will not come to know about it. Okay, if it is being tapped, there is still some chances based on leakage. You monitor the power, you put sensors, but to an extent, right? And that is the reason we'll see in while traveling in trains, you will see the security guard carrying those keys. They are physically carried. Okay, so this is the challenge which quantum key distribution is trying to solve: generation of keys at both the ends. Okay, so the ideal rules for the security would be that the encryption key, because see, the entire game of quantum key distribution is it talks about the keys, the cryptographic keys. Okay, and in quantum cryptography we are talking about symmetric key cryptography. So if I'm saying encryption key, that means the decryption key is the same. Using entanglement superposition, we will be using the correlations there to generate the correlated bit strings at both the ends, which will eventually form the encryption and the decryption keys. So key should not be copied. This is ideal situation. They should be random enough. Key tampering should be detectable. This is desired. Okay, but we know the limitations of classical world. If we have tried using a mathematical hard problem, but the quantum computer, once it becomes um, a fault tolerant, realizable, a useful quantum computer, will be able to break it in few seconds using some kind of a hybrid algorithm, which will primarily use Shor's and Grover's kind of cryptographic primitives, algorithm primitives. And so this is a challenge. Computational security, again, while designing the security model, nobody had thought about the quantum computers or infinite resources. Okay, so that is again a challenge. There is no no practical classical solution for key distribution. And then, of course, we rely on a algorithm or a pseudo random number generator. So these random numbers are generated with some mathematical uh, using some mathematical algorithms, and which has a seed. So, and that seed, depending upon the seed, it repeats itself. So again, if the seed gets repeated, then it is no longer a useful key. On the other hand, quantum security, it guarantees you it makes certain promises. So what are they? They say the quantum world says that, the quantum keys, which means quantum entities, microscopic entities actually carrying the key information. So they're carrying the binary information. So those keys cannot be copied or they cannot be cloned. These are the rules of quantum mechanics, and we'll look into it later in these slides. Non-locality. This is again a fundamental principle. Perturbation of an unknown arbitrary quantum state is detectable. So if anybody is trying to monitor the state, it will throw some light on the state. Okay. So, and it will change its property. So in the quantum world, any mischief can be identified. Okay. So that is the reason we are saying that quantum will give you a solution of future proof, but future proof or a provable quantum security. So I was just, talking to Pillai about, if you have, you have gone through a lot of quantum sessions, but maybe we'll pause here, because the idea of bit and a qubit is very important. And when in quantum communication, qubit for us would be a photonic qubit. It's also known as flying qubit, because we are trying to communicate from one place to the other. And you can communicate only when the photon or the light will go from one place to another. That is the reason for communication, any type of quantum communication, photons are used. Photons are quantum entities. And even for building a quantum computer, some properties of photons are used, but quantum computers are localized, and quantum communication can be from one, it can be done with spatially separated objects. So just to tell you that, when a classically we represent, because information is physical, right? So when we try to encode or depict a zero binary, logical zero, logical one, we define some thresholds, voltage thresholds. So there we say it is logic 0 if it is within a certain threshold, and logic 1 for input and output. In quantum case, we have qubits, which is quantum analog of bits, and we represent using direct notation, get 0, get 1. This is a block sphere. Again, I think you have already you have some background about the block sphere, the linear algebra. So I'm going to leverage on that, and it also simplifies my life. But again, I'm tempted to tell you, how would you relate a qubit with a photonic gadget? So this is get psi, an arbitrary quantum state. Now this is get 0. Get 0 and get 1 are quantum states, and these are computational basis states. Alpha and beta are the complex numbers, and they tell you with what probability you'll be finding the state in logic 0, in get 0, and you'll be finding the state get 1. Okay, so now I can represent this using a beam splitter. A beam splitter, as the name goes, splits the beam into the transmitted path and the reflected path. Now, now I'm just imagine the alpha is it's 1 by square root of 2. It's a complex number. I didn't really want to write it in kets. So alpha is 1 by square root of 2, and mod alpha square is half. Okay, and beta square is half. So this will become half of get 0, half of get 1. Get 0 is my reflected path. Just like voltage levels, we have defined the logic 1 to be the reflected, logic 0 to be the reflected path and logic 1 to be the transmitted path. Okay, so if there is an arbitrary photon here, but here we will not take arbitrary. Let me say we are taking a superposed diagonal state, ket 0 plus ket 1 by square root of 2. And if you are sending that one photon through a beam splitter, had there been 100 photons, it would have taken 50 of them would have taken the reflected path and 50 of them would have taken the transmitted path. But if there is a single photon, then the chance of being in both the path is half. I hope I could make it clear, right? So this is my reflected path, this is my transmitted path, this is half the probability. So the chances of finding the photon in the reflected path in the transmitted path is half. Now, this is interesting also because these are the kind of experiments which you can do in your lab to convince yourself about the existence of a photon. You will be tempted to believe that, well, the photon may be going, the ball is going sometimes in the reflected path, sometimes in the transmitted path. Well, you can question, right? Then what you have to do is you have to build an interferometer. Okay, if you build an interferometer, which will be something, a beam splitter coming here itself and meeting it, so the state, the quantum state which is traveling, which has its presence in both the paths, will be actually meeting itself in the second beam splitter, and obeying the laws of interference, you will be seeing the output. So that is one way of making yourself believe in the beautiful physics which you are seeing. So now here we'll talk about superposition. Now, in the quantum world, we are talking about quantum superposition. Of course, superposition exists in the classical world also, but here we are referring to a quantum superposition. And again, I think you must have looked into the maths of it. Here again, we just gave you an example of a superposition states where it exists in both the paths simultaneously. Now there's a boy in the class. Sir is asking a question to give him an example, to give an example of superposition, quantum superposition. And the boy says, a mermaid. The teacher asks, well, but nobody has seen it. And the boy says, it's simple because the moment you try to observe a mermaid, it gets collapsed to either a girl or a fish. Okay, so now the professor is in a, I mean, he's actually a professor, right? I mean, so he tells that if, and I think you'll be able to appreciate because you have gone through the lectures now of, and you know, a diagonal state and a computational basis state. So he says, if there is a basis where mermaid itself is a state, here he is referring to the diagonal state, then if you do measurement in the diagonal basis, then you will be able to see the mermaid. It's a beautiful example, and this is from one of my, so my professor has, he writes books, and this is from one of his pages in the books. So now, since you have seen what is a superposition, you know the idea of a qubit. So, so we did a simple experiment, a small experiment. So this was again motivated by a student who had come to me. She always comes and challenges me, and she has made this. She wanted to make this simulator. Now, what should I be doing? I mean, if she's making the simulator, then I should be doing something useful for her. So we came up with this idea that let us work on a middleware and the backend. We work on single photon sources. So this is a process called spontaneous parametric down conversion, where we generate single photon sources. So so this is a laser. So when the laser light is falling like this, it is going through a crystal and you are getting daughter photons. Now, one of the photons is going to a detector. The existence of the single photon, it gives me the confidence that the other photon is also, it's coming as a pair, it's pair. Now, there is a lot of, engineering and a lot of efforts which goes into it in designing this. But anyway, so we could separate out the path of a single photon, and we can use some gadgets like half-wave plate, polarization beam splitter to run some experiments like quantum gates on the path of the single photon. And we have here two detectors for detector 1 and 2, which is for logic 0 and logic 1 state. And now let me show you this demo. Now, since this is a quantum experiment, unlike the classical one where a NOT gate can be represented by a transistor and you just do one result, but here you have to do several, because these are photons coming, you have to take the average. Okay, so if I'm sending some, here I'm sending logic 0 and there is a NOT gate here, you can see you're still getting some counts, and you're still getting a higher counts in logic 1. So you are inferring that the output is logic 1. In your IBM Qiskit, they may not show you these counts, but it's the average count which tells you that this is your logic 1. And this, of course, forms a part of probability. And G2 is the second order correlation function. Now, this is again, if you have the second order correlation function less than 0, then you confirm to the standards of the light coming into the quantum regime. And let me now start the demo. Okay, so you have the okay, so now just before I begin, let me tell you that this experiment was done live. And we were doing this experiment, the hardware was in our lab, and the gates and all instructions were given from first floor of our building, and our lab is in the third floor of this building. So we were randomly choosing between these quantum gates, and the corresponding command was going from via our network to the um, to the quantum circuit hardware which is there. We were collecting the data, and then the results were published. You will see words like latency here. You will see the simulation. Simulation is always 100%. You will see the real-time result. Just please remember that if I'm sending identity, then my output of logic 0 should be logic 0 only, right? So you will see number of counts of logic 0 higher and logic 1 lesser. So that would mean that, okay, so it has started. Measurement is completed. You can see logic 0 is the highest. Now count logic 0 is 6,000 and logic 1 is 300 counts. Okay. Then we will be applying a NOT gate. NOT gate. So simulation will show highest probability 100% for logic 1, and we'll wait for the experiment to get completed. You will see maximum counts 5,779 in logic 1, and it was less in logic 0. And I'll tell you why we have those residual counts also. Hadamard is a superposition gate. You will see that half 50% probability of 0 and 1 in simulation. But if you do a quantum experiment, practical experiment, then you will see 5,800, 5,600. So almost similar, but not exactly equal. So those numbers forms part of the probability. Okay. And you were seeing those residual counts because of the non-idealities or of the detector, which still gives count when it sees no light, or, so these are called dark counts. So there are some unique properties. They do not have 100% efficiency, so there are challenges with these detectors, which becomes very interesting when you're looking at it from an eavesdropper perspective. How can he use these how can he leverage these loopholes, to extract maximum information from a quantum key distribution setup? So understanding all these instruments, and all of them are actually classical gadgets only, but when I'm reducing the intensity, or here exactly we have done the spontaneous parametric down conversion, where we generated quantum light. So when the quantum light interacts with these gadgets, then we observe um, you know uh, beautiful results come out of it. So we'll talk about entanglement now. I hope I'm audible, right? uh, I should not keep on speaking and then finally realize that there was no network. Please give me some sound, if I'm audible and we are connected. um, so okay, so yeah, okay, audible. Thank you so much. Yeah, so I'll go back to my presentation, and I was talking about entanglement. So in entanglement, the story started around 1905 with when Einstein said that energy cannot be discretized and there is a unit energy, and he was talking about photons. But he was also a little puzzled. He was trying to understand the nature of the quantity and quantum entity, and he was questioning, that can quantum mechanical description of physical reality be considered complete? And why was he saying that? Because of certain principles like non-locality, non-realism, that were challenging the classical understanding. So that is the reason, he wrote this paper in 1935, and in 1935 there was another paper talking about the consequence of wave function collapse, and I'm talking about this gentleman, wave function collapse, and that came to be known as Schrodinger's Schrodinger's cat. And uh, and and actually this it was the Schrodinger's cat which gave the name, the central property of EPR paradox, as entanglement. So both of these things happened in 1935, and now uh, now the work published by both of these scientists it actually inspired many, and one such person was Bell. And Bell started investigating whether the whether local hidden variable theory is compatible with quantum mechanics. Okay, so and then he gave an inequality that must be obeyed by uh, any local hidden variable theory, and that is known as Bell inequality. Okay, and it's wonderful, and it's actually very interesting to understand the inequality, how it is derived. And now there was Clauser who had come up, and he had given he was fascinated by Bell's paper, and he tried to try to construct the inequality in a way that it can be experimentally tested, and that is known as the CHSH inequality. Uh, so um, so once it is, and it was experimentally tested, and it was found that the inequality, quantum mechanics or any quantum states actually violates that inequality. So what has happened is, there was an idea. The idea was evaluated, analyzed. The idea was, it proposed, brainstorming was done, it was analyzed critically, and then there was experimental tests which were performed um, to uh, to to understand how the quantum system behaves, and whether the inequality it satisfies or it doesn't satisfy the inequality. And after that, what happened was, once you know that you have actually generated the entangled state, you're playing with quantum entities. So then you start doing an application of entanglement goes to quantum computing, quantum communication, generation of random numbers. And I'll tell you one beautiful experiment on how to, how you'll be able to generate random numbers. You can also try that logic of generating random numbers using entangled states by IBM, which is freely available. But if you look at this state, in 2022, Zeilinger, Clauser, and Aspect got the Nobel Prize for quantum mechanics, and you have our honorable Prime Minister, sir. With Zeilinger, I think the book is named "Dance of Photons," and you can see the importance, the political importance. Okay, so the let us look at the entangled state. It is H stands for horizontal, V stands for vertical. This is ket xi, which is an entangled state. Subscript 1, 2 means it is a two particle state. Okay, two particle state. Earlier we had seen a single particle state, right? If you see, this is a single particle state. Okay, but here it is a two particle state. Again, 1 by square root of 2 has come in place of alpha and beta, which means half of the times, if you have an ensemble of say 1000, you will see 500 times it is you're observing an HH states and 500 times you're observing a VV state. Now, if there are 1000 such events, you do not know what is the next event. There is no information, or there is no such correlations which will lead you to predict the next event. Okay, if the first event, the entangled state collapses to an HH, the next measurement can be a VV as well. It has equal chance to be a VV. Okay, there is no biasness, there is no correlations. So this is how the mathematically intrinsic randomness is um, is challenged. Okay, so when we say that an entangled state is intrinsically random, this is how it comes from. Now, leave aside the loopholes, the non-idealities of any physical device. You will never get 50-50, so there will be some biasness. And then, of course, when we try to do any application, you have to take care of those remove those biasness. Here it says that it exists as an entangled state and it is not a separable state. Anything which is not separable. Okay, entangled state is something which is not separable. It doesn't separable. Now, it has lot of interpretations. Now, let us try to look at why Einstein was not comfortable. So if you have H in this galaxy and you have the other particle in the other galaxy, okay, and you have you have a lot of entangled states between Alice and Bob. This is something, should I be? Okay. So if other galaxy, so if on measurement, first measurement, I find that I have got an H state, then the other particle, which is in the other galaxy, instantaneously, I should not be using the word instantaneously, or say I should say rather say simultaneously. It will be H. But if and on other measurement, if I'm getting a V, then the other state in the other galaxy will also be a V, and that will happen simultaneously. Okay, so how can this information travel so fast? How is it so simultaneously, and how is the particle in the other galaxy, he's trying to predict what is the measurement of the first state, so that he has to also follow, he has also to follow, because there's a correlation which is happening. So this is the beauty of entanglement. Now, again, there are some small exercises which I have given to help you understand, the maths of the entanglement, because this itself is an exercise for students, that how you analyze mathematically whether the state is entangled or not. Okay, so you take a generic state and then you expand it, and then you try to just see under what conditions um, it is entangled. Okay, but then you will come across such such equations. For example, one of them is mentioned it here, that you will find it will be very difficult to come pinpoint the two variables which will actually lead to entanglement, and then you will say that fine, I mean, a separable state, uh, an entangled state cannot be written as a separable state. Okay. Now, this is the entanglement setup. um, Okay, so when I had shown you about the earlier setup, it was also generating two photons, right? Correlated photons. But these two photons are not entangled. It actually depends upon the type of crystal I'm using. Crystal selection, orientation, polarization. It has a lot of things has to be taken care of to generate the state which you want to. Here it is a signal and idler photon. This is not entangled, okay? And I'm using only one photon. The other photon is going to the other detector, okay? And the detection of one photon has no influence on the detection of other, okay? It is separable. But if you are looking at the entangled state, these two are entangled state, HH plus VV by square root of 2. and so a measurement of one has an influence on the measurement of the other. Right now, they're on the same table, few centimeters, 30 centimeters apart. Okay, but we have experiments. The first quantum key distribution experiment by Bennett was in a distance of 30 centimeter, and today we have 1,000 kilometer, right? So this is again the laser passes through some filters and mirrors, and it goes through the crystal. We generate the entangled photons. We separate the path. It is a non-collinear, which means there is a angle. The photons are coming out through an angle of 5 degrees from the central pump beam. The pump beam is intense. It has to be stopped. The ratio of entangled photon generation is 1 in billion. And these are the detection module, and each of them goes to some detectors. Now, a small experiment. Okay, let me also tell you. So when I'll be showing you this demo again, no? So the signature, the visual signature of entangled photons is the intersection of two rings, you know, so you have one of the entangled pair coming from here, and its other pair coming from here. So once we generate the photons, we try to capture the ring, and thereafter very systematically we try to focus on the central regions on these circles. Okay, and what you will be seeing in this demo is we will first generate this visual picture, and we will destroy the phase matching condition. So this happens when we satisfy certain energy momentum criterias, and we reach a phase matching stage. If the matching stage is disturbed, then the ring disappears. Then it's a classical light, and we lose the quantum light. Okay, so now I will show you this demo. Now we have to do this experiment in by making the ambience as dark as possible. So right now the experiments are not running. It's only the classical light. Detectors are off. So when we will do this experiment, the lights will go off. This is how the setup looks like. Now this is the MCCT camera, and you will see the light coming from here. It is going through the crystal, and then we are capturing the image. You can see the ring, the intersection point of one of the rings. I think now we will be showing you the intersection point on the other end. So this is done by my team members, and we have done so many demonstrations that, and you can see that very, very nicely and smoothly they have brought the camera to focus on the other intersection. Now we will disturb the phase matching condition. Once the phase matching condition is disturbed, the rings will disappear. See, the rings are disappearing. Okay, so there is no quantum light right now. Again, they will bring back the phase matching condition, and the intersection will again appear. Right. So for all our experiments, we have to zoom into those intersection points, because the rest of all the light which we are collecting outside that intersection point is a noise, and it will lead to errors. So again, if you're trying to, do some kind of extraction of information like an eavesdropper, there are a lot of things you can play with and see, how it affects the security or the quantum QKD error, which we say. So these are some of these. We have to characterize the entangled source and tomography visibility, and finally the Bell violation. So we have calculated I was talking to you about this inequality, right, which was proposed by Clauser. So we have performed this experiment, and we have attained a value of 2.679. 2 root 2 is 2.8. So anything quantum is greater than 2 and less than 2 root 2, and we have obtained a value of 2.679. So this is the CHSH inequality. These are the different polarizations which we are rotating to obtain the parameters for the inequalities. Now, So we now, okay, now let me tell you how to generate the random number from this entanglement. Okay, so yeah, so if suppose, so designate HH, measurement outcome HH, as logic 0 and VV as logic 1. So on subsequent measurement, you will be getting 0 1 1 0. Okay, and say suppose you have done some 1,000 measurements, so you will get some thousand events, and you will find that if you count total number of ones, total number of zeros, it will be approximately near to half. This is the reason, this is the interpretation of 1 by square root of 2. Okay, but there is no correlation existing between the first and the second and the third event, or so forth. So it's a forward secure way of generating random numbers. So we had generated those numbers, and right now if you scan, it may not work because okay, but then we generated them, and we had tested them using an ENT test suite, and the results were coming quite close to the ideal expectation. So now we have actually made a test bed. So since I have come from this background, and I had tried a lot of efforts went in my graduation, in my when I was working in Bose Institute, I was actually working on a lab. So to do the entangled setup and the single photon sources. So we do not get trained manpower here. So we had to start by doing fundamental experiments, superposition, entanglement, characterization. So we have built a test bed. Okay, and the test bed, you can see the entanglement generator and the detection module. And in this test bed, you can actually generate random numbers. You can generate entangled sources. You can generate random numbers from entangled. You can also do a QKD. So, and we are trying to pitch it for universities and center of excellences for quantum technologies, because once a student has an idea about the generation, when they make their hands dirty, actually, that is where they can actually contribute to this technology. At the moment, most of the things are not manufactured in India. So here you have this nonlinear crystal towards characterization. This is a laser source, and this is going through the experimentation. This is the generator module, and this is the detection module. Now, some benchmarks which we have done against the some of the standard results. So now let us try to talk about why we are so sure about the security of quantum key distribution, and how is a QKD protocol developed. So one of the preambles is no cloning theorem. So it basically means that you do not have a quantum Xerox machine. I think before going further, would you like to take maybe for 2 3 minutes, you would like to ask any question, or if there is any question, then we can you know so in the chat window, if I can see some questions, I'll be happy to answer. Otherwise, I'll then start. So Lalita madam, I hope my slides were changing. You have written at 4:49 that they were not changing, so but right now I think it's fine, right? um so okay, so how random numbers are generated. Um, as so, let us say you want to generate random numbers using the first picture which you had seen in the presentation, the beam splitter and the single photon. Okay, so if the single photon comes and it goes to a beam splitter, you have the transmitted path and reflected path. The photon is present in both the paths, but upon measurement, it will randomly collapse. Okay, to um, either one of the detectors, either the transmitted path or the reflected path. Okay, so now you give a binary number to say anything detected on the reflected path is logic 1, and anything detected on the transmitted path is logic 0. Okay, and then you do some random measurements, so you will start getting 0 1 1 0 based on where the photon is getting detected. Because remember, the photon is in superposition of both the paths, and upon detection it collapses to either one of the paths, which is randomly, and I'm using that random uh, principle to generate binary number string, bit string. Is this clear? Okay, great. Yeah. Yeah, so we are actually working on tutorials and basically the educational toolkit. I think tutorials anybody else can also do, but what I'm trying to bring forth is an educational kit, which will help colleges and students to actually make their hands dirty with the technology. Okay, how many qubits are needed for random numbers? One qubit, one random numbers. Now there are entropies, like if you're doing time encoding or you're doing multipath superposition, then you can have more random numbers from one measurement. That is also possible. Again, you can use entanglement to generate random numbers. You can use different properties of the photon for generating random numbers. Okay, so I think now I'll go back to the presentation. Okay, so now let us see what are the principles. Um, what are the principles when we say that the key distribution is secure or key is safe? What do we actually mean? How do we say that? First principle is there is no quantum Xerox machine. If there is a, for example, let there be a quantum Xerox machine, okay, and you have ket xi, which is a some paper, uh, something printed on a paper, and then you put a blank paper along with the blank paper, you insert it in the quantum Xerox machine. What you will be expecting is the blank paper also has a footprint or a copy of what was sent with that printed paper. But in a quantum Xerox machine, it doesn't happen, okay, because of the linearity principle of linear algebra. Okay, it is not possible. Now, for example, to have a clearer understanding, let me say that let there be a quantum Xerox machine uh, which will be cloning ket psi, and there be another, and the same Xerox machine should be also be able to clone ket phi. Okay, so you cannot have different Xerox machine for different states. You need to have one universal quantum Xerox machine, right? So let there be that Xerox machine, and I would like to clone these two states. Now, if you take the inner product, okay, and you do a little maths, what you will find out is that you cannot duplicate any unknown quantum state. This sentence itself is very important. You cannot duplicate any unknown quantum state. You can duplicate a state which is either equal or orthogonal to it. For example, I am sure you must have heard of C0 gate. If you have a logic 1 in the control side, control part, and you have logic 0 in the target part. So since its control is 1, so 0 will invert to 1. So at the output, you will have uh, 1 1. Okay. So that is an example of a NOT gate, but you can also use a C0 gate to do some kind of fanning operation. But again, that is not for universal states. It is limited to only either the state and the state which is perpendicular to it, orthogonal to it. So in short, there is no way of copying an unknown quantum state. Now, since we are running a little late, so I would, so this is just a same message as in the quantum state cannot be cloned. It's called non-orthogonal states cannot be discriminated with certainty. And this was used by Weisner. I think he was the first person to propose quantum money. where he used the non-orthogonal states, and Wouters and Zurich had mentioned, has a beautiful paper on a single quantum state cannot be cloned. So it actually explains this point only, that it is because of the linear nature of quantum mechanics, such cloning mechanisms are not possible. So now here we again go to non-commutivity. So here we'll talk about the position momentum. We know that it cannot be simultaneously measured with certainty. Okay, and we will use this principle again. Now let us try to understand this with very simple explanation. Now, in this experiment, what we do is we have now if you are closing slit 2, then you will have a probability distribution curve like P1. If you are closing slit 1, you will have a probability distribution curve like slit 2, like P2. Okay. Now, if you have both these slits open, which means the quantum entity is actually traveling through both the slits, okay, then we get interference-like pattern. So this is a quantum signature. The moment, and this happens only when you are when both the slits are open, which means the electron is actually coming out from both the slit, and it is giving an interference signature. And if somebody is trying to monitor the position, or say from which slit the electron has passed, it collapses to a bell curve. Okay, it's a classical signature. So if nobody is trying to observe the state or monitor the state, then I'm observing a classic quantum signature. But the moment anybody is trying to identify, look into the state, shine light, try to find out from where the electron has come out, such disturbances will perturb the quantum state because it's very fragile. Okay, and it will reduce it to a classical signature. So the quantum cryptography, as it's mentioned here, it's all about that. As long as there is no perturbation, no disturbance, you will see the quantum signature, and then that will ensure the security, because no cloning, principles like no cloning and all, no, it will not allow any particle to be duplicated or anything disturbed or monitored. But the moment somebody is doing that, then it will collapse to the classical signature. Now, this is again something which we had seen before, but this is from a quantum cryptography perspective. Something which I would want all of your attention here. It's very simple, but certain terms I'll be using, which I want you to remember. Here, a message is sent either from Alice or Bob, or Bob or Alice, depends. I mean, these are the cryptographic couples, but we can write a TX and an RX. So between two QKD nodes, I think that will be proper. They are connected via a quantum channel and a classical channel. So a quantum channel is where the quantum light is passing, the quantum states are passing, the photons are passing. Okay, it can be free space. Free space would mean that there is no medium except air, or it can be vacuum, where I'm sending the light, generating the light at Alice's end, and Bob is having the detection module. And the other channel is the classical channel, where I'll be doing the post-processing. In none of these channels, I am actually distributing a pre-generated key. Okay, so when in my next few slides, you will see how the keys are being generated using correlations of entanglement or of superposition. So Alice and Bob are connected by a secure classical channel. Now, a secure classical channel means it is pre-authenticated, and I'm only solving the problem of key distribution. Okay, and nothing more than that. the person eavesdropper can listen to any information which is being sent from Alice to Bob using classical channel, but eavesdropper will not be able to tamper anything. Okay. Then in the quantum channel is considered insecure quantum channel. Why? Because the quantum eavesdropper. So you have, I don't know if I have mentioned here, but a quantum eavesdropper is different from a classical eavesdropper. Okay, a quantum eavesdropper can use any technology which the physics allows, quantum physics allows. It can take out a photon, look at it, it can keep it back, it can modify, it can do any kind of an attack. It is actually categorized what are the capabilities of a quantum eavesdropper. It falls in under three categories, depending upon if he has a high dimensional quantum computer along with a quantum memory, high dimensional quantum memory, or if he only has a quantum memory but he doesn't have a high dimensional quantum computer. And if he doesn't have a quantum computer and if he doesn't have a quantum memory, then what are the quantum eavesdropper attacks which is possible? So there are entire categories. Okay, so all of them actually target quantum channel. They do not target classical channel. Okay, so classical channel is secure. You can listen, but you cannot
Ma'am,
tamper. It is very important. Hello.
ma'am, your slides are not visible.
Okay, let me. Um, is it visible now?
No, ma'am. Yes, ma'am, now visible.
Okay, so I last 5 minutes it was not visible, is it?
Yes, ma'am.
This was visible.
Yes, ma'am, now visible. Now perfectly fine.
Okay, okay. So I'll tell you very briefly. I mean, I hope the no cloning theorem was visible, right? Okay, I hope I was audible. That means
Yes, ma'am. Ma'am, you were audible. Only the slides are not visible. You were perfectly audible.
Okay, so I was talking about this, Xerox quantum Xerox machine. I think the maths is has been, all written. So if you can glance through, perhaps maybe later also. I was trying to tell you that there is no quantum Xerox machine, and I took the examples of say we have such a Xerox machine where I can clone ket xi and ket phi. Eventually, if I'm opening them up using doing the inner product, we find that it is actually very limited scope. I cannot duplicate an arbitrary quantum state, but I can only duplicate a state which is either equal to or orthogonal to it. And these are the papers by Wouters and Zurich and Weissner's paper on conjugate coding. They were the first people to propose how this feature can be used for quantum cryptography. And most of the quantum cryptography, QKD, are based on the fundamental principles of no cloning or using non-orthogonal states. So I tried to explain how quantum cryptography using Heisenberg's uncertainty principle by saying that if the electron is, if there is no disturbance, it is taking both these slits, paths from both these slits, and I'm seeing an interference pattern. If I'm closing any one of the slit, then I'll be seeing a bell curve, which is a classical probability curve. And if somebody is trying to monitor whether the electron has come from either one of these slit, then it collapses to a classical signature. So the principle of quantum cryptography or quantum key distribution is based on using non-orthogonal states, because I'll not be able to find out I'll be introducing some errors because I'll be changing the property if I'm doing some measurement without knowing the state. So that is one. And the second is the no cloning theorem. Here, these two channels are very important. Please remember, the classical channel is a secure classical channel. The quantum channel is an insecure quantum channel. There are three categories which I had already mentioned. Encryption algorithm, decryption algorithm would be anything based on which uses symmetric key cryptography. And that's it, I think, yeah. Now we'll talk about QKD. Now, there are two ways of doing, two methods. One is prepare and measure, and the other is entanglement. For prepare and measure, you can refer to the picture which had shown, where I generated single correlated photons using the laser light. And for entanglement, you have the entangled photons. I have shown both the demos. The structures are different because entanglement, one is the transmitter and there are two receivers. So the QKD is performed between two receivers. The quantum transmitter transmits, generates, and emits the entangled state. The two receiver will capture it. So it will have a triangle kind of a relationship. And then the prepare and measure is somebody generating, encoding, and sending, the other person receiving it and then doing the measurement. So these are the two different states. Then we have measurement basis. For example, these are the polarization basis, this is the rectilinear basis, and this is the diagonal basis. And I hope you are familiar with these two bases, because now we are going to do a little bit of cryptographic activity using this colored balls which represent a vertically polarized light, get 0. Gray ball represents a horizontally polarized light. So I have written here question 1 because I want you to think that if there is a gadget, and in that gadget I am sending rectilinear polarized light, that gadget can correctly tell me whether it is horizontal or vertical. So again, I'm repeating, I know the state I'm sending to the receiver. I'm sending a horizontal or vertical state. I'm using a polarization based beam splitter. So if I'm sending a horizontal, I will be getting it in the transmitted path. If I'm sending vertical, I'll be getting it in the reflected path. So my encoding, decoding is proper. Whatever I'm sending, the receiver is receiving. Okay. Similarly, I have a green ball and a blue ball, which stands for diagonal basis states. Okay. These two states are orthogonal to each other. Similarly, red and gray states were orthogonal to each other. If I'm having a ball, because I will be sending the ball, I know what I'm sending. So I told Bob that this time use a modified polarization beam splitter, which will have some additional optics to differentiate ket plus and ket minus. So if I'm sending a green ball, it goes through that modified optical, beam splitter. And if I'm sending blue, I'll get blue. If I'm sending green, I'll get green. Okay. Now, all these colored balls can also be represented. I could have represented it here as well. So these are the 4 polarization states. And this diagram is to tell you that red and gray ball, they are not orthogonal to green and blue. Okay. So now you remember the non-commutativity. So you'll not be able to measure red ball and blue ball with same measurement instrument because they do not commute, and I have done the maths for you here. Okay. Similarly, gray ball and green ball do not commute, but red ball and gray ball, they commute. Therefore you can identify them with certainty. Green ball and blue ball, they commute. You can identify them with certainty. See, the entire crux of the cryptography comes from these mathematics. So if this is clear, cryptography is just a execution of one step, and it will be anyway clear. So this understanding has to be correct. Okay, so the two bases, I told you about a beam splitter, polarization beam splitter, and a modified polarization beam splitter to differentiate between the two states. So now in this slide, what I was trying to tell you, that if I'm sending a red and a green ball through, say, a measurement device, I'll not be able to differentiate the color. What will eventually happen is, okay, let me tell you in the next slide what will happen. So this is my measurement, PBS. So if I'm sending a horizontal and vertical, I'll be getting them clearly. If I'm sending a blue ball and a green ball, I'll be getting correct outputs. Okay. So I usually make we make a magic box kind of a system here. So we say that each side of the box corresponds to one of the measurement. And in classical box, you have those states there, and whichever side you open, you will always see a red ball is a red ball in the classical box. But if you have a quantum box and you have put a red ball inside and you gave it to Bob, and the Bob does not know what ball is inside that, and he mistakenly opens the plus minus side of it, okay? So what he sees is a blue ball, okay, or a blue ball or a green ball randomly, okay? Similarly, if I put a gray ball inside it and he by mistake he opens measurement, or he does a diagonal basis measurement, in other words, he will be seeing ket plus and a ket minus state, or he will be seeing a blue color ball or a green color ball. So what has happened is the initial information is now destroyed because of incorrect measurement. Earlier, what was the case? If I'm having a red ball, I open M01, which means I'll do a rectilinear basis measurement. I will get the correct state. The information is retained. But because of incorrect measurement, the color of the ball has now changed. Okay. So just imagine a case where I'm sending 100 red balls, and Bob is, randomly opening either of the two sides of the boxes. So 50 times he will be seeing correct red ball, 25 times blue ball, and 25 times green ball. Okay, this is a just exercise which I have just made, but it is again based on the mathematics. So such examples or such questions can be formulated from the understanding of how these maths work. Okay, so now if you want to understand it simply, if I'm asking the right question, or if I'm having the right measurement equipment, I'll always get the right answer, which means my information is not destroyed. Okay, but so here again there was a diagonal state and I have used a modified polarization beam splitter. I'll be getting the correct answer. Okay, but if I do not tell Bob, and Bob randomly does measurement and he has the incorrect basis, then the horizontal state will become diagonal. So this doesn't happen in the classical world. In classical world, any measurement you do, red ball stays a red ball. But in quantum world, if you do incorrect measurement, the state gets changed, the input gets changed, information is lost. So similarly, so these two examples forms the basis of BB84 QKD. Okay, so here we understood that the right question, right measurement, we get right answer. In fact, there is no error, we get correct state. Wrong answer, which means we do random measurement, and this you can relate it with eavesdropping or Bob doing random basis measurement. Okay, so you will get half the times correct and half the times you'll get errors. So since Alice only knows the correct question, so during error correction, there's a step called error correction. So they then share information, and in fact the information which they share, they always discard those bits. They don't incorporate those in the keys. So now how do I convert this technology to application? So basically we were discussing application since we started talking about QKD. So here is BB84 QKD. BB84 QKD comes under prepare and measure. And it is now this should be very clear, because the earlier examples were meant to make it to simplify the understanding. You can see rectilinear basis here and here. So in rectilinear basis you have a logic 0 for the horizontal, and in diagonal basis you have logic get 135 as logic 0. For logic 1, for both the bases you have to designate logic 0 and logic 1. Okay, so for logic 1 you have vertical as well as 45-degree polarization. So now Alice is selecting random numbers, and she then, this logic 1 can be anything. It can be a vertical or it can be 45 degree. It can be vertical or a 45 degree. Logic 0 can be horizontal or it can be 135 degree. Okay, so Alice then she chooses the basis randomly. So logic 0, 2 bases, logic 1, 2 bases. She chooses them randomly. So this is how this photons come out to be. And then when they reach Bob, now here again we have considered something very ideal, because because these signal is in picowatt, 10 to the power minus 12 watt, okay, and they are very fragile, and the fibers are birefringence. So there will be certain certain properties, some error introduced, some absorptions which will happen. If you are sending millions of photons, you will get some thousands of photons depending upon the attenuation and the distance between the two. The detectors are 10% efficient, 60% efficient, so you will be losing photons there as well. The mean photon number is 0.1 in case of prepare and measure, which means you will observe of a photon is in existence for every 10 pulses. Okay, so all that reduces the key, the length of the cryptographic key. Okay, and then you have the random basis. I hope now this should be very clear, because Bob will be doing it randomly. He has no information what state is coming from Alice. So 50 times, we have seen it earlier, right? That 50 times in case of incorrect measurement, they will be randomly correct or wrong answers. So this you'll have to apply it here. And finally, when Alice will tell Bob which one to keep and which one to not to keep. Key is not shared. You have to understand what kind of an information is being sent from Alice to Bob. Alice is sending the bits randomly encoded. Then Alice is also telling which are the basis, which basis of Bob is correct or matching hers. She does not tell about the key or or the encoded state. She only shares basis information, and from there the keys are derived. Okay, and that is the reason I was telling you that the keys at both the ends, Alice and Bob, will be derived or generated. There is no pre-shared. Okay, and whenever they are matching, they come out with a correlated, partially correlated bit string, which is called as sifted key. So this entire key architecture looks like this. You have the protocol. This is the QKD protocol. So the entire quantum transmission is reflected here, quantum data transfer. So from raw key, you come to sifted key. From sifted key, sifted is nothing but it's actually matching the basis at Alice and Bob's side. Then Bob will be sending a part of the key to Alice to find out whether how much is the error, is it within the threshold or not. So what does that mean? Because the components are non-ideal, because it is very fragile, because the efficiencies are very poor, because there will be a lot of absorption. So you will anyway introduce some errors in your normal transmission. Okay, so and this is the reason why you need a very good engineering and a good control over your devices. Okay, because these loopholes can be used to mimic certain errors by the eavesdropper. So the error correction, this is not the quantum error correction which happens in quantum computers. This is classical error correction which happens on the data which has been generated from after quantum data transfer. So if it is more than the threshold, now what do I mean by that? Do I have a slide on that? No. So what does it mean is, you can try doing a intercept and resend attack here. Okay. So you will see that the error increases to by 25%. Okay. So the sharp increases because shows you that somebody is trying to eavesdrop or monitor the channel. Okay. So those kind of activities are characterized here. If it is more than threshold, it is dropped. If it is less than threshold or within equal to threshold also, then we proceed for further analysis that how much information has gone through while error correction. Because as I told you, that we'll be sharing a part of the key with Alice. We will not be using it, but we'll be using it to estimate the error. Okay, so how much of the information has leaked there? All that has been analyzed, and the security parameters are calculated based on how much information is a photon in photon level also, because if there are multiple photons in a pulse, then each photon will have the same information which can get leaked to a quantum adversary. So it is very important to maintain the quantum signal strength to the quantum regime. okay, or using an entangled photon source, or using a single photon source. Then privacy amplification is there, and then we have the final keys. So in error correction, as I told you, a segment of the received raw key is sent to the sender, is shared with the Alice, and then Alice will do the XOR, some matching, find out the threshold error. So there is a noise, Shannon's noise list coding theorem, which tells us about the minimum number of keys that is to be publicly exchanged. Okay, now there is no particular algorithm, but as I have written here, that there is now an error correcting algorithm should be ideally close to this limit. There is no prescribed algorithm. Okay, usually Cascade or LDPCs are used, and again, there is no 100% assurance that it will correct all the errors, because you are using a sample of the randomly generated string to estimate the error for over the entire distribution. So that kind of a study is also needed. See, each and every aspect of the QKD architecture is itself an intense research work, as, and the toughest being, I think, the security. Okay, it is not very easy to come up with a quantum key distribution protocol, because as I told you about the strengths of all the adversaries, that has to be accounted for while formulating the amount of leakages or the information between the Alice and Bob, comparing it with the information with the eavesdropper and the Alice. So fine, there is techniques, unidirectional or bidirectional error correction, which can be used, which can make it approach the Shannon's limit. So let me not go through it. I think at this stage, photon encoding is quite clear, and then encoding here, I'll just quickly take you to the type of encoding. Here all the time I was talking about the polarization, and I'll stick to that. But actually there are different techniques to encode the binary information on the photon. It can be spatial mode, it can be path based, it can be polarization, it can be time also. It can also be time bin encoding. And these are just few. There are several more. Orbital angular momentum can be used as one of the degrees of freedom. So there are a lot of protocols in the literature. If you do a literature review, you'll come across different techniques of encoding the qubit. Most popular of them is actually polarization. And so based on the encoding decoding mechanism, usually if I'm using a standard telecom fiber for 1550, I'm doing terrestrial QKD, then usually we go for phase encoding. Okay, and in phase encoding for a decoder, you need an interferometer. If you're doing polarizer, based upon again how your encoding setup is, your decoding could be a set of optics with quarter wave plate, half wave plate, and a PBS. So it all depends. Now, in fact, it's also interesting to know that there are techniques of doing quantum cryptography even without sharing a key. There are techniques of doing quantum cryptography without sharing something physical between the Alice and the Bob. It is called counterfactual quantum key distribution. So it's a very broad topic, but I would like you to, enjoy the subject. So I would start with something. I've started with something very similar. We need to understand prepare and measure and entanglement based. So I have discussed one such protocol. Another prepare and measure protocol is B92, Bennett 92 protocol. In BB84, you had seen here 4 states, right? 4 non-orthogonal states. Four states were used. Yeah, 4 states, right? Ket 0, ket plus, ket minus, ket 1, okay, ket 0, ket 1, ket plus, ket minus. All 4 states were used. But now in B92, there is an optimization, and it's very interesting to understand. It is only 2 non-orthogonal states are used. Okay, it is using the non-orthogonal property. It is using the no cloning theorem. You cannot clone a non-orthogonal states with certainty. So it is using both. Here it is a little different than other protocol, because here the encoding of logic 0 is on, as you can see, is on H, corresponds to logic 0. and it's and diagonal corresponds to loss plus, get plus. But on the detection side, if I'm supposed to get logic 0, I should be getting get minus. So there is a polarization conversion which happens, and there is again a mathematical reason to it. It will be interesting if you can figure that out. What it will involve is actually you have to open the state get plus is equals to get 0 plus get 1 by square root of 2. Get minus is get 0 minus get 1 by square root of 2. And when you open this state up, and you will figure it out why uh, this kind of maths is used, that if I'm sending get 0 here, then the sure way of getting get 0 here is actually detection of get minus. If I'm sending get 1 here, get plus here, then the sure way of getting get plus on the other side is actually get 1. Okay, and these two are actually bit 0 and bit 1. That's why I was talking about get 0 and get plus. Okay, I think I have done a little bit of maths here for you. You can refer to the slide, and if there is any difficulty, I think I'll be happy to come back. But once you open this up, it explains that why getting get minus is a sure way, of getting get 0. So if Bob measures, just remember that. Okay, so if Bob measures get 0, then it can become get 0 or get plus. Get plus is in computational basis of, and it will collapse to 0 and 1 with 50% probability. Okay, but if Bob measures 1, then it is for sure that it is coming from get plus. So if you have any probability issue, then please I'll be happy to come back. But these are simple maths which you can do at your end. This is one such schematic, and if you visit this website, it allows you to play with B92 QKD platform. You can give different polarizations, and it also has an opportunity to to mimic Eve, what Eve can actually do, and and then what kind of detection is there. It also tells you about the number of keys and errors and probability. So it's a good exercise. Try sending 100 bits and find the probability of accepting a single bit. Okay, fine. So these are some small. So this is how a setup looks like of B92. You have a source, you have the encoder, you have decoder, measurement. This is control electronics and communication engine. Please ignore D. So as I told you, it's connected by a quantum channel and a classical channel, and there is a synchronization. So you have already taken a peep into the optics part. So the layer consists of the passive optics, optoelectronics, mechatronics, compute engine boards, all sort of things are here. But the two transmitter and receiver are also connected by a time synchronization, because these needs to be picosecond, nanosecond level synchronization happens here. Okay, so now we have done this experiment in our lab, and now this is how it looks like. It is a transmitter node and this is a receiver node, separated by a distance of 34.5 centimeter. And these are the states which I had discussed with you. This is the optical setup. There are two lasers to generate the plus state and the get 0 state, logic 0, logic 1, and its corresponding polarization state. And you have the detectors here. This is the Bob module, which will capture the light, and it will do the corresponding measurement in these detectors. They have a TDC fitted with it, and then there is an analog to digital, which conversion happens. Okay, so in this module there are a little more optics, more than B92, because we are actually doing aerial quantum communication. So there are some more lasers around here. I would like you to attempt detection of an eavesdropper. So if there is no eavesdropper, the probability of accepting a single qubit is 25%. Now, position an eavesdropper between Alice and Bob, and and this is one of the strategies which I have actually figured it out. But you can also think of any more strategies, and it will be nice to see that how the error or the probability of accepting a signal bit changes once an intercept and resend attack is done. And it actually gives a reflection of or the signature of somebody monitoring the system. Okay, I have also given the result. So Bob accepts 37.5% of the bits, and if E was detected, because its acceptance rate is 12.5, higher than expected. But then I think it will be nice to try this first, and then see if if you can arrive at these numbers. And I would like you to also do an intercept and resend attack for a BB84 protocol, and see how the probability of error increases. So these are some of the results from B92. When, as I told you, I'm sending binary logic 0. Okay, so I'm sending logic 0 encoded in get plus state, which is a diagonal state, and and I can say that I'm receiving the logic bit 0 with certainty if I'm observing a, get 1 state. Okay, get 1 is a vertically polarized state. So it's an assurance that I'm getting logic 0 with certainty, and these are the experimental results. Okay, so this is a string. I'm sending logic 0 for 1 second, perhaps, or a little lesser than 1 second, and this is the output. Similarly, so these are test cases. Similarly, I'm sending logic 1 for some time, and logic 1 is written as a get H, which is horizontal state, and it's and I can be assured that I'm certainly detecting logic 1 if I'm detecting get minus state, okay, which is an anti-diagonal state, and it corresponds to logic 1 at the Bob side. Now, if I'm sending random numbers, then I can see at random distribution, and they are also occurring at almost equal time. So that also tells you that lesser number of bias, and I'm getting equal number of logic 0 and logic 1. Now, let us quickly look into how an entanglement based QKD would be looking like. Entanglement based QKD, basically there are two such types. One is Bennett Prasad Mermin 92. This is the year. So as like in any entangled state, it's a two particle state. So you will either have HH or VV, or HV plus VH. Those are the states. And Alice and Bob will be doing, so they will be, so here please note that Alice and Bob are the two receivers. In the prepare and measure, Alice was the transmitter, Bob was the receiver. But in entanglement based QKD, Alice and Bob are the receivers, and there is a Charlie who is a transmitter. So Charlie transmits, Alice and Bob receives. They will be doing some random basis measurement, rectilinear basis or diagonal basis, as you can see it here. And based on the measurement, they get some results. Okay, and if the bases are same, as you can see, Alice and Bob are using the same measurement equipment. If Alice is using polarization beam splitter, Bob is also using a polarization beam splitter, good, it's a good story. But if Alice is using modified PBS, which is meant for diagonal basis states, and Bob is using um, polarization beam splitter, which is meant for rectilinear basis measurement, if such combinations happen, they have to discard. So this happens during sifting when they talk about their results, about the basis which they have used. And yeah, again, this inversion is again depending upon the type of, there are 4 APR states, no? So it depends upon which state you're using, that you have to do the inversion or not. And finally, the BBM92 is we're generating entangled state. So an entangled state, if you verify it first, so that means that any communication, as long as the states are entangled, there is no scope of any eavesdropping. Otherwise, it will satisfy the inequality. Remember the Heisenberg's inequality, which I had showed you, that if there is no disturbance, then the quantum signature is received. So here, if there is no disturbance, then my Bell inequality is violated. If there is a disturbance, my Bell inequality will no longer be violated. I know somebody has monitored the state, or somebody is observing the state. So we are doing this experiment in lab, but I could not capture the image. So here is a simulation. I think it's also a good work because it gives you an idea. Remember the intersection points? I'll play it again. Okay, it just doesn't take my permission to start. So here there is a laser. From the laser, I'm generating the entangled photons. You have to assume that it's generating entangled photons after this non-linear crystal. So light is coming one by one. Photon is represented like a ball. It doesn't really happen that way, but just for an understanding, light is coming out of it. It is going through two mirrors. Then it is coming through the type 2 babio crystal. I'm getting entangled photons. You will see the photon, the intersection points. Remember the one which I had shown you in the demo? The light is being captured from those points. And then there are two detectors. In the picture here, I showed you very close by, right? But it can be in two separate buildings. They can be a kilometer apart. Okay, it can be between, if you have at some sometime if you have the station in moon, that you can do an entanglement distribution between moon and earth station. So you can think like that. Hmm. And so you are doing a QKD between the moon station and the earth station. Okay, so this is something like that. So you have a satellite, a transmitter is in the satellite, and you are doing a QKD between one celestial body and maybe one earth station. Yes. Okay, so let me just if this will repeat. Huh. So you will also see the change in wavelength. From 405 it becomes 810 nanometer after it goes through the SPDC. It's a down conversion, so wavelength is doubled, frequency is halved. It goes to the detector, then you get the symmetric keys. Secure communication established. In ACCHE-91, let me not go into it deeper. Here, the setup is chosen such that you have there is a provision of testing whether the state is entangled or not simultaneously, which is not there in the BBM92. So I ACCHE-91, it uses these measurement three basis states. Okay, so first they do a pair generation, which is very typical, which I have shown you earlier also. Then they do random measurements, something similar to BBM92, but it is in three basis state. After that, again, there is a public basis disclosure. After every photons have been measured, Alice and Bob communicate over a public but authenticated classical channel to compare their basis. This is, I think, clear. When they have the same basis measurement, those states pass on to the shifted basis state. So key generation happens from the correlated outcomes. But here, at the cost of higher security, 1/9 of the entangled pairs result in the key bits. So the key size is less. And of course, the security verification is via a bell test, which is the a distinct feature of ACCHE-91, and it's one of the highly secure quantum key distribution protocols. So now what we are actually working is, now if you want to take it to society, to reach out to to different stakeholders and around the globe, what will eventually happen is there is a QKD in the from space to the terrestrial network. There has to be a connection between them. So here the UAVs or the drones play a very important role. So what we are working in here in CDAC is building quantum aerial platforms. So we are working with industry in making quantum drones, which is PQC enabled, quantum communication enabled. So we put the Charlie entangled state. At the moment, we are doing B92 using two drones. So we have the quantum transmitter sitting on the drone payload and the receiver sitting on the drone payload. They both will fly up and they will communicate and will exchange keys, and then they'll come down. But such kind of a technology will help us take care of many of the limitations of direct line of sight or terrestrial QKD, because terrestrial QKD you cannot you are dependent on the terrain. If the terrain is not good, you cannot lay fibers. You need something in there in free space. You Again, it is not practical to build ground stations everywhere. So and drone offers you reconfigurability, all time, all area coverage, which is unlikely with with satellites. Satellites, they do have they do cover thousands of kilometers, but they are available for a very short time, and not on when you require it, it may not be, because it actually follows a period, right? So aerial platforms yeah, are lucrative. They will be like quantum relays. So uh, what will eventually happen is a link between, from terrestrial to drone to high UAVs, to high altitude platforms, to satellites. Such a link is, and the world is actually moving in that direction. Now, to achieve this, we would require a lot of engineering from different disciplines to to bring state of art technology, to understand the loopholes, to work around it. So such activities are there, and has happened in Nanjing, China. I'm particularly talking about aerial QKD in and US, Ohio University, and in India, TIFR is working on the balloons, high altitude platforms, and we are working on uh, quantum key communication with aerial platforms, for example, drones. So this is prepare and measure drones. Remember the B-92, and this is the entanglement based drones, where you have the Charlie on the drone and the two receivers on the ground. So this is, I think I'm almost at the last slide, or second last slide. This is the market survey, and these are the products in the Indian market, above the dashed ones, and below are the global products in the global market. And we have recently been awarded Director General Award for core research, where we have made this entanglement, a test bed, a free space quantum entanglement test bed for different applications. Okay, so this is essential for giving a hands-on, or for actually developing a quantum fundamental system, not only from the application perspective, also from the education perspective and for engineering perspective. Yeah. And I think, and this project has also given me opportunity to do a lot of demonstrations, and we have been showcasing, or we have been participating in Science Day in Aero India, and so forth. Yeah. So thank you. In PKI, the random number needs to be checked for a random of checks to be served as a key. Is quantum computer used to do that also, such as to be a prime number? So in quantum cryptography, or in quantum communication, the random numbers are generated from a physical process, not from a PRNG. Okay. Um, I'm not very sure what you're trying to say by number of checks to be served as a key. But yes, if you're indicating the quality, can you hear me? I mean, again, there's a silence. Uh, I hope the slides, and I was also
You're audible, audible very much.
okay. 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 Yeah. So here I really don't understand what you are trying to talk about the checks, but this is a physical random number generator. See, QRNG generates physical random numbers at one place. QKD is nothing but a QRNG at two different places, you generating random numbers using correlations in superposition and entanglement. And the entropy and all has to be verified before using it for any cryptographic purposes. So here we observe its change state, how many these features possible to work on, but we have to decide before working. Sir, I'm not very sure what you're asking here. Without instruments, how can one proceed with quantum implementation without instruments? So one thing is, you can look into the Qiskit tool. I was also using Qiskit some some 12 years back, when they had just 2 qubits, then 5 qubits. That gives you an idea of, on the maths, build some confidence on the maths and the cryptographic primitives. See, I was talking about quantum cryptography, but there's a lot of primitives in quantum communication. For example, superdense coding or teleportation. So those primitives can be implemented and tested. What is essential is the maths behind it, and the fidelity, on how you actually arrive, or how it is benefiting, how it is performing in comparison with the classical. Teleportation is also possible classically, right? But the fidelity is higher in the quantum. Something like that. Yeah. I hope you found this useful, or if there is any suggestion for me, I'll be also happy to take it as a feedback. Yeah, sure, sir, sure. We'll be happy if you can send me an email. I think, yeah. Thank you. Yes, Pillai sir, I think.
Yeah, if there are any question, yeah, I think there is one question.
IBM AER simulator also generates random numbers using quantum computing for QKD, similar to quantum physical quantum machine. Yeah, I see now you are using random numbers for cryptography, so you cannot rely on a distant source unless you have you have a very secure means of communicating from the quantum machine to your end. So that is the reason we are building it on table, so that it can, because it's a requirement. Otherwise, it's a quantum physics, so you can generate random numbers from Qiskit, from IBM open source physical devices also. Rigetti or anybody from Amazon, it can be generated. Privacy amplification is amplifying the mutual information between Alice and Bob, or reducing the information between Alice and the eavesdropper. It primarily finds out the security, how much security is a collision probability. They find out the collision probability, and from there they derive the amplification, the shrinking factor, which is known as the privacy amplification factor. Is there any use of algorithms like Kyber, dilithium? Yeah, because as I told you that we are using a secure quantum channel, a secure classical channel. So a secure classical channel, you will be using all state of art. For authentication, you can use PQC. So, but for quantum key generation, such algorithms are not used. But while communicating to each other classically, you may want to use a PQC also in that. So Kyber, dilithium, for authentication, those can be used. Random number generator, different approaches. Yes, you can generate random numbers using superposition, entanglement, time encoding. There are different methods. Using different properties of quantum, it can be generated. When we observe its change state. Yes, when we observe it, how many such features is possible to work on, but we have to decide before working. Yeah, I mean, yes, when we say the state changes, I give you a very beautiful example. When there is a different basis measurement, or you have a quantum box, you are doing different basis measurement. It cannot be infinite. How many such bases are possible in 2 dimension or in 3 dimension? Those have to be understood first. Then we know that how many such state changes can happen.
Yeah, thank you so much, participants. I think there has been a lot of excitement and the thought process that is there. And yeah, I have been going through the chat. You can see the appreciation. Thank you, ma'am. Thank you for the enlightening session once again. And we would hope that you will spare more time in the next few sessions. That's what we are looking forward, because you've been part of the preparation of the syllabus. So they are about all of them in this course. All of them are faculty members actually. So that is one of the key takeaway. Earlier they were different people, but they are all faculty members here, and they are all excited to start that. Yeah, you can also contact CDAC has been working with a lot of experimentation mechanism. So we are also in touch with them. So you can talk to ma'am and then find out how you can look at some of the equipment, some of the experiments that they are conducting there, and you can try to take it forward, right? Thank you so much, ma'am. And I think maybe one last question, we'll take it from Lalit. Ma'am, you can take this as the last question. Yeah, we'll conclude with this last question, ma'am.
Okay, so what are the quantum network topologies being used in your experiment? So here we are only doing a link, one link. So we are not using topology. We will be creating, or we will be experimenting with different topologies using our link. Okay, so our is just a transmitter to a receiver, one link. Again, using an entanglement based receiver to receiver, another link. So in a network topology, you have multiple users, or a hub and spoke kind of a model. Those things we have not done. We will be doing it in future, or we'll be putting our link there in some topologies which can come up. Quantum state is very sensitive. Absolutely, it is very sensitive. It is sensitive, I mean, because and this manpower is not there. The skill is also not there. Training is not there. It is indeed very difficult, because you have to make the photon follow a particular line parallel to the table, same height from the table, and the direction of the polarization, distortion we have to consider. We have to consider the profiling of the laser. So there are multiple aspects, multiple considerations we have to account for. Many times it's an R&D, so many times we also do trial and error and experiment with different gadgets, and then we arrive at a solution. So those also adds to the novelty. Distortion to either we rectify. There are some works on correcting it, scrambling polarization, and then correcting the polarization. So yes, there is way, but we cannot do it for every entirety. We have to give it. We have to allow some errors actually. Though it is difficult. Okay. Oh, because of distortion also it can be encoded. Yes, because any distortion is nothing but kind of a measurement. Okay, so it can be distorted because of it, and that actually counts in the errors, because the distortion has happened automatically, and the initial state was with Alice's knowledge. So if something has happened incorrectly, and there is again a set of random measurements involved in the bob. Okay, so there will be footprints, there will be some indications on the error which has gone into because of distortion, because of environment perhaps, and that is the reason I say a better engineering, a hardened system is what will be actually useful. Otherwise it's just experiments. Okay, I think, sir, I now yeah, I need to wind up now. Sir, I cannot hear you.
Yeah, thank you so much, ma'am. I think you also taken extra time, and yeah, some of the questions you can post it to us. We will take the solutions from ma'am. Ma'am has to also take a break. So we will conclude here. We will meet tomorrow at 3 o'clock. We'll continue with Dr. Jaykumar Vaidishankar, the simulation aspects. And yeah, the questions, the last question we'll post back to ma'am, and then we'll take response from her. Thank you so much, ma'am, for joining, and we hope that you will continue to be there in the next few courses that we will try to conduct, especially. Thank you so much, and we'll take a break. Yeah, thank you, ma'am.